Today, I'm going to be talking about esoteric web application vulnerabilities. Basically, that means strange vulnerabilities. Vulnerabilities which are difficult to identify and sometimes difficult to exploit. A little bit about me. I work doing source code reviews and application penetration tests, and I've been doing that for like 10 years. I'm a developer. I code in Python, and some people know me for the W3AF project. That's an open source web application security scanner, but I'm not going to be talking about that today. And I use open source and stuff. So let's first try to understand why these complex vulnerabilities are important. SQL injection is going to die soon. Frameworks like Ruby on Rails, Django, and many others are all using ORMs. So if you're a developer and you are coding a new application, you're not going to be writing a select statement on your own. You're going to be using an object, and you will write something like object.select, object.find, and if you use that, it's very difficult to have SQL injections in your web application. So SQL injections right now, they are becoming rare. And something similar is going on with cross-site scripting. If you use modern web application development frameworks, most likely that framework uses a templating engine. And the templating engine is going to help you, the developer, avoid cross-site scripting. And basically that happens because if you have the template like this, the templating engine, when you do something like this, user.url, and you use the curly braces there in order to print the value of that variable, it's going to, by default, HTML encode your variable. So if you are a developer and you write this, there's no cross-site scripting. You need to write extra code like adding a pipe raw or a .html safe or something like that in order to add a cross-site scripting to your application. If we take this into account, we are going to notice that kind of the common vulnerability types are slowly going to disappear. So we need to find new things. And those new things is what I want to talk about. And of course, I don't care about those boring vulnerabilities disappearing, because I want to find interesting things. I want to actually use my brain. I want to outsource the detection of the boring vulnerabilities to tools and use my brain for something fun, interesting, challenging. So I'm going to walk you through 5 different vulnerabilities. These don't have anything to do, any relation between the vulnerabilities. So just let's start with the first one. Aggressive input decoding, which is going to lead to no SQL injection. This aggressive input decoding is something that happens at least in Ruby on Rails, but I believe it also happens in development frameworks in Java and Python. So let's see what happens. First, we have the source code for the HTTP request handler. That source code is a code snippet from a Ruby on Rails application. And what happens there is that we have the params variable. This variable is going to be filled with whatever the user sends in the HTTP request. And the interesting thing here is that param is going to be filled with different sources of information. For example, if we send the information in URL encoded form, it's going to end up there. Or if we send it in application JSON, it's also going to end up there. And if we use query string parameters, guess what? It also ends up in the params variable. So that's good. It's a feature. Developers are going to use it in order to abstract the sources of information. But there is something interesting which we could do, and that's sending an HTTP request with a post body like this. And if you noticed before, what we were seeing there is that the name variable was a string. And now we are modifying it a little bit, and the type of that variable right now, it's a hash. It's a Ruby hash. That's a good feature. Let's move into something different, and then we'll add up these two things in order to get a vulnerability. When you use a Mongo database in your Rails application, you're going to most likely be using something called Mongoid. Mongoid is just like a driver around a Mongo database, which is going to allow you to query the documents that you're storing there. It's just like using an ORM for SQL. You use an ODM, such as Mongoid, for Mongo databases. So if you're writing a Ruby on Rails application, you use Mongoid, and you're going to have a code similar to this one. You'll have the registration model, and you're going to query the registration model using this syntax. In the syntax, you say, all right, I want the registration where the user is this one, and the confirmation token is this other token. If you're using Burp, or if you're using any other proxy to intercept the HTTP request, you're going to see this request, which is handled by that code. Everything works. That's just a feature. And let's understand how a developer could perform a little bit more advanced queries into the Mongo database. That's going to be performed, for example, like this. Users where your user ID is something, and the country is not equals Argentina. Or user ID is in a list. So I suspect that you guys see where this is going. Basically, what we could do as part of our attack is to combine the two different things. Combine the aggressive input decoding that we saw before with the NoSQL injection and the filters that we were seeing. So if we have this code and we send this request, what's going to happen is that here we are forcing, and actually with the application JSON and everything, but specifically here, we are forcing that the value of the token variable, it's actually a hash. That hash is passed here, and the developer was not expecting this. So what happens is that you're able to complete the registration without knowing the token. That's a specific case of a NoSQL injection, which is possible because of what I mentioned before. All right? Any questions? Cool. So how do we fix this? Developers need to fix it because it's serious. It's something that can be exploited. It's something that can be detected using source code review, can be detected using black box testing. And depending on the context, this can be exploited to get kind of serious things. So in order to fix it, developers need to add to each params a dot to string. That's going to transform whatever comes from the wire and whatever is decoded from the HTTP request, it's going to transform it to a string. As you can see from this, the fix is not complete. The fix is actually really bad. Developers are going to forget to add the dot to string to every params that they take. So there has to be a different way in order to fix it. And there are two different ways, which are complete and more kind of architectural solutions to this issue. The first one is to use Sinatra param. It's a gem that you use in Ruby on Rails, which is going to allow you to perform strict input validation. So each of your HTTP request handlers is going to have kind of a header that says params name needs to be a string. And if you don't do that in your HTTP request handler, you get an exception. So that's a good way, because in each of your HTTP request handlers, you need to define the types of the variables. If you don't do it, it's going to break. So that's good. And there is another way, which is to use something called strong params. That's basically the way that Ruby on Rails uses to fix SQL injections, but ported to Mongo databases. Also, that's a gem. You need to use it. You need to integrate it into your project. And it's going to prevent tainted variables to go from the user to the database. OK, next one. I was doing source code review of an application. And this application had two-factor authentication. The two-factor authentication was done using a phone call. So when a user wanted to perform a specific action in the system, the application simply called the registered number for that user. And after doing that, you picked up the phone, and over the audio from that call, the application told you a code, you got that code, and you entered the code into the application. All right? So as part of this test, what I wanted to do was to bypass this two-factor authentication. This system, one of the things that it did was when you created a new user, it has to verify that you actually owned that phone that you were associating with your account. So the vulnerability that I'm going to tell you is in that process, in the process of verifying that you actually have your phone with you and that you are not associating a random phone number. OK. So basically, the user says, please verify my phone number. The vulnerable web application goes to a software as a service. This software as a service is the one that actually makes the call. This is something like Twilio, for example. Twilio is going to perform an HTTP request to the vulnerable web application asking for the audio for this call, because Twilio doesn't know what you want to send in the audio for the call. And finally, Twilio, or any software as a service, is going to perform the call and once the phone call is connected, it's going to send the audio with the code. So the user sends the code to the application, and the identity is verified. I tried to identify different vulnerabilities in this process. I tried, of course, to perform brute force of those codes, and it was not possible. After the third try, it simply asked me to enter a CAPTCHA. After the try number 10, it blocked my account. So it was okay. I tried kind of different ideas, like, all right, I could maybe verify the account of, verify the phone number of a different person, like hacking the smartphone for another person and stuff like that, but it was kind of complicated. So the best choice that I had was to hack the vulnerable web application, which was my actual target. So I said, all right, I'm going to try to directly access the URL from which the phone call audio comes from. And the URLs looked like this. These URLs were randomly generated here using a unique ID, and as an attacker, I was unable to know the next unique ID. So it was impossible for me to perform an HTTP request and get the audio for a user. And even if I was able to do that, I had no idea if I get this, the code that I get from that audio, I don't have any idea for which user it is. So it's kind of useless to just brute force this. So I started to investigate. I was doing a source code review, and I said, all right, let's try to understand how this works. From the vulnerable web application, there is an API call to the software as a service that performs the outgoing calls, and it looks like this. It's a phone number, and the audio callback is in this URL. The audio callback is where the phone audio is, of course. And I was digging a little bit further into the implementation, and I identified the vulnerability somewhere in those lines. Who can tell me where the vulnerability is? The callback URL is, yeah, it's a parameter for start call, but I, as an attacker, cannot control all of callback URL. I can control a part. With the host, all right. So here's the vulnerability, and how can we exploit it? We can exploit it by changing the original HTTP request to something that looks like this. So I changed the host to evil.com, and what happens next is that instead of Twilio going to the vulnerable web application to get the audio, it will go to my application, like evil.com. From evil.com, I get this unique ID, I go to the vulnerable web application, get the audio, get the code, and then send it back to Twilio, and Twilio doesn't actually know what happened there. So this was possible because of two different reasons. First, the developer used request.host in order to create a callback URL. That's usually a bad practice. Then something else is that the web server in front of the web application was not properly configured. So if your in production and you're serving a web application, you need to define a whitelist with all the domains for which you want to answer HTTP requests. So if you have Nginx, for example, you just create a whitelist with all your domains, and for the domains that are outside that list and for which you receive HTTP requests, you just drop them. Also, in this scenario that I was testing, it was a Django application, and it was poorly configured, because in Django you have something called allowed hosts. Allowed hosts is a list of hosts for which you want to answer HTTP requests. And that was poorly set. So because of all those reasons, this was exploitable. Did you guys follow me? Yep. All right, next. So password resets are really sensitive. And developers tend to make mistakes in password reset implementations. So if you're ever doing a source code review, spend time in password resets. The good thing about password resets is that even tiny mistakes, like the ones that I'm going to explain to you now, might lead to account compromise. So just to freshen up your mind, in case you never forgot your password for any application, when a user wants to perform a password reset, what happens is that the user goes to a web application, he clicks, I forgot my password, and he chooses, he enters his email address, and the application is going to send an email to an email address with a link for the password reset. That link is going to contain a token, randomly generated in most scenarios, a randomly generated string that's going to be used to reset the user's password. So the implementation actually looks similar to this. We have two different parts: the start password reset, which is the HTTP request handler that's run when the user enters his email address. This is start password reset. And the second part, which is complete password reset, that's when the user follows the link that was sent in the email and sets his new password, and the token is received, the new password is received, the password token is reset, and so on. So this is the implementation, and what we are seeing here on top is the database attributes or columns that we have in the user model. So for this to work, what needs to happen is that the user will have, the user model in this application will have an attribute, and that attribute needs to be the password reset token. This password reset token is just the unique ID that's sent to the user's email. So in the user model, we add a new column called password reset token. That's a string, and we default it to nil. This nil here in Ruby is going to be translated to a null in the database. All right? So let's just imagine that this is a MySQL database that the Ruby on Rails application is using. So this nil translates to null in the MySQL database. So start password reset, complete password reset. Basically, start password reset, what's going to happen is that based on the email address provided by the user, we generate a random token, we set the token in the model, and save it. That goes to the database. Finally, we send the email to the user, and by sending in that email, we send the token. And here, what we see is the second step, which takes the token, sets the new password, sets the password reset token to nil, and saves the model and sends in the user. So there's a vulnerability there, and the vulnerability is a little bit hard to identify first. But basically, what's possible to do by knowing that Ruby on Rails is going to perform this kind of aggressive input decoding that I explained before, is that an attacker can send token null. That token null is going to be translated into here, params token. This is going to be nil in Ruby, and when it's sent to the database, it's going to be null, like null, N-U-L-L. And what happens here is that when an attacker sends this HTTP request, this query to the database is going to return the first user in the database for which the password reset token column is null. And we said here that by default, all the users, all the new users in the system have null. So by sending this HTTP request, an attacker is resetting a random user password to let me in. The good thing about this complete password reset implementation is that the last step is to sign in the user, because it makes sense, kind of, it's okay, because if you know the token, it's because you received the email and you're the owner for that email address, so you are the user. So why not, in the complete password reset, we just sign you in? So this was a real case, and I was able to run this a couple of times, and I got access to the first 10 random users in this application. I didn't know exactly which users they were, but I just ran this. I got access to the user's account. By gaining access to the user's account, I got access to the user's email. I started a new password reset flow for that user. That changed the column, the password reset token column in the database for that user to something different of null, and then run the attack again. That was going to choose a different user than the previous time. By repeating that, an attacker could gain access to multiple user accounts. Basically, all of the user accounts that don't have a password reset flow in progress. Okay, how to fix this? There are two ways of fixing this. This, as I said, I don't personally recommend it because it's very easy to forget to do this two-string cast. Or the other way is setting a good default for the password reset token. A good default in this scenario means something that's not null. All right? Cool. Okay, so something that I really love is integrations between merchants and payment gateways. So developers are always under pressure project leaders are pressuring them in order to deliver features, and usually they don't care about security. And that's shown always in these integrations with third parties, where, for example, we're going to see that's possible to perform something called a double spend. So let's see how it works. When you're on a merchant site and you have a Pay with PayPal button, what's going to happen is that the user clicks on that button, goes to PayPal, pays for the services or the goods that he's trying to purchase, and if everything went all right, the browser is redirected back to the merchant site, and you see a page that says something like, thank you very much, thank you for your purchase. In 3 days, you're going to receive your goods, your shoes, your T-shirt, whatever you bought. Behind the scenes, something that's going to happen is that PayPal is going to send an event to the merchant. That event is going to be sent under a protocol that's called IPN. IPN is a way in which PayPal sends a lot of data to the merchant using an HTTP post request. And all of those pieces of information that are sent from PayPal to the merchant are very well documented and have a lot of kind of tips and tricks which you, the developer, need to implement in order to make that IPN implementation secure. So how is this implemented? Basically, if you're the developer, you go to your PayPal settings and you say, okay, I want to receive my IPN messages, events in this URL. And you, the developer, need to code something here in PayPal handler. And that PayPal handler usually looks like this. Like we said, the user clicks on Pay with PayPal. The user goes to PayPal and then pays using his credit card, and PayPal sends a post request to the IPN handler. And what should happen next, and that's something that in some cases is forgotten by the developers, and it's a completely different vulnerability, is that the developers don't check that the request that they received is actually from PayPal. So in a secure implementation of the IPN handler, what a developer must do is everything that he received here from PayPal, he must send it back to PayPal and verify it. The verification process is just to avoid that an attack in which an attacker is going to send arbitrary data in order to fake a payment, okay? So in this verification, PayPal says, all right, verified, and the payment is processed by the merchant. This HTTP request that goes from PayPal to the merchant looks like this. It has a lot of parameters. The ones that we are going to care about are these 4 parameters. We have the gross amount, which is the amount that the user paid in PayPal. We have the payment status. Basically, it means that the payment was successfully made by the user and the charges were made to the credit card or not. Like completed means yes, and incomplete or unsuccessful means no. Then we have the receiver email address, this, and custom. So the receiver email address is the email address for which the event is for. So when PayPal receives a payment, that payment is for a specific PayPal account. That PayPal account is this one. Finally, what we see here is a custom. Custom is basically a way for the merchant developer to track payments. So when a merchant creates a new button on their site, and the user clicks on their site, they go to PayPal. And there, as a developer for the merchant site, you lose track of all of the payment that's done here in PayPal. You need a way for tracking the IPN event with the user that clicked on the button. So as a developer, you use custom. Custom, in most scenarios, is the user ID in the system, the user's email address, or the ID of the card that's being created. So this custom is basically the user's ID. And we already talked about this, all right? The verification process. In this case, we have an insecure IPN handler. This insecure IPN handler performs all of the steps that I talked about before. It basically receives all the parameters that we saw on the previous slide. It will go to the PayPal URL and send all of the parameters again. In the response, it will check if it's verified. That means that all of the received parameters are OK for PayPal. And if it's verified, then it processes the transaction. Otherwise, return an error. Who can spot the vulnerability there in that slide? Perfect. All right. So I'm going to explain what he said in slides. You didn't listen, but he was completely perfect in his vulnerability description. So what's missing here? What's missing is a check to verify that the event that we are receiving is actually for our merchant account at PayPal. What could happen here is that an attacker can follow these steps and perform a double spend. And the steps are, first, the adversary or the attacker creates a new PayPal account. He configures an IPN URL pointing to evil.com. He creates a pay button using custom equals unique purchase ID. This unique purchase ID or the user ID comes from the merchant site, and that needs to match in order for everything to work, because if they don't match, this params custom is not going to work. That line is not going to work, so they need to match. Then what happens is that the attacker is going to create a payment to himself. He's going to use the Pay with PayPal button that he just created, and using the attacker's credit card, he's going to pay money to himself, to his PayPal account. So that happens here. When he does that, PayPal is going to send all of the IPN data to his IPN URL. The attacker receives that information, and he sends it back to the merchant. That should be the other way. So the adversary sends the information that he got for his merchant, all the event for his merchant, and he sends it back to the vulnerable IPN handler. because the IPN handler is not verifying the receiver email, what's going to happen is that it will send back the information to PayPal, and the event is going to be verified, and the payment is processed. This is just the same thing that I explained before, and the fix is this. As a developer, you need to add this line in order to check that the receiver email that you get in the parameters equals to the merchant email address in PayPal. Okay? Right. So one of the most common questions that you receive after explaining this is this PayPal's fault? And actually, the answer is no, but maybe yes, because their API design was poor, and because of that poor API design, they are kind of moving the responsibility of checking and making security decisions to the merchants. And let me explain this with a secure API design. So I work for some guys in Argentina that created something called Mercado Pago. Mercado Pago is a payment gateway similar to PayPal. And what they did is to create a different IPN protocol. In the IPN protocol that they use, when a new event is triggered by users paying in Mercado Pago, what happens is that instead of sending all of the information from Mercado Pago to the merchant, what these guys do is just to send an ID of that event. What happens next is that the merchant needs to get that ID, get the API key for Mercado Pago, and go query the API for Mercado Pago events. From that API, they get all of the information. So even if an attacker is sending events to that IPN handler for Mercado Pago, what's going to happen is that when the merchant queries the API is going to say something like, no, you don't have access to this event. This event belongs to a different user. And that's right, because it belongs to a different user, because I was trying to make an attack. So PayPal made an incorrect design decision which leads to these types of vulnerabilities. Okay? Great. Last one. Let's check how much time I have. Cool. Number 5. So in Ruby on Rails, there is something called active support message verified, message verifier, which is a feature of Ruby on Rails, which allows you to take a message, sign it, and then, if you want, on the other side, take the message and verify its signature. The problem with the message verifier is that it could lead to remote code executions. And I found 2 different instances of this vulnerability in independent source code reviews. So once you sign a message, the result looks like this. The result is the base 64 encoded version of the message here, dash, dash, and the signature. And the messages can be decoded. So you get, it's not encrypted, it's just signed, and it's base 64 encoded, so you can take the message, it has some things there which are kind of indicating that it's not a simple string that's encoded there, and it's actually marshaled and unmarshaled. So one of the cool features of message verifier is that you can sign and serialize or marshal any object. So if you have, for example, an array, you have an object, you have almost anything in Ruby, you can serialize it, sign it, and send it over the wire. So the serialization process is done using the Marshall module for Ruby. And as you guys might know, if you have been doing source code reviews in Ruby, what happens is that, what happens is that the Marshall module is kind of insecure, because in the documentation it says something like this. Unmarshalling arbitrary data is insecure and will lead to arbitrary code execution. So, as an attacker, what's preventing me from creating a specially crafted string that's going to be unmarshaled by the application when it receives this message? What's blocking me is just a secret that was used for signing these messages. So this secret depends on the developer. And in the two cases that I identified, one of the secrets used for signing these types of messages was "hack me, I feel lonely," and the other one was the user's ID, which was a number, like incremental number, integer. So as an attacker, what I can do is to follow the steps. Just brute force the secret until I identify it, or if maybe I know it somehow because I gain access to the source code or something. Then, as an attacker, you create a specially crafted gadget. That gadget is basically going to be an object serialized using the Marshall protocol that when you unmarshal that object, it executes an arbitrary command. Then, using the secret that I got from step 1, I sign this gadget, I do base64, and I send it back to the application. When the application gets that message, it's going to verify the signature. That signature is going to match because I got the right secret. And afterwards, the application is going to unmarshal the string and remote code execution. Okay? So this vulnerability is similar to ones that you might have seen in Ruby on Rails cookies. If the secret for a Ruby on Rails application is disclosed, then you can follow kind of the same steps here. And the vulnerability is fixed by using long secrets for signing messages, or even much better, using a different serializer. So message verifier takes a optional serializer parameter. By default, the serializer is marshal and unmarshal. And if you use serializer JSON, what you're saying there is that instead of using marshal, you use JSON, and there's no known vulnerability that's going to take you from unserializing JSON data to remote code execution. So the fix is to have long secrets, and to change the serializer. So basically, that's why I don't care. I don't care about kind of silly vulnerabilities and boring vulnerabilities disappearing. You guys shouldn't care either. This is much more fun than a SQL injection. And you are smarter than your tools. Let your tools perform the automated work. Let your tools try all the cross-site scripting tests on all of the parameters. And use your time to perform source code review and identify these types of vulnerabilities. Usually, you're smarter than your client. Try to convince your client to provide you with the source code. You're going to find more vulnerabilities, and your security assessments are going to be much more valuable. And finally, you're smarter than the developers, or you know more about security than the developers. And you're going to be able to identify these vulnerabilities and many others that they are going to keep introducing, even if the framework is protecting them against cross-site scripting and SQL injections. So that's my Twitter account, my email address. Thank you.